AP Calculus 4.5, day number 2. Topic for today is linear approximations. Our goal for you today is that you will be able to approximate any function using this linearization method. So a review of differentials from yesterday. Pause the video and see if you can fill in these blanks. Okay, so delta x and dx represent the change in x on, and oops, wow, that should be an x. There you go, x, not a triangle, on both the function and on the tangent line. And now delta x specifically is just the change in x on the function. Okay, delta y is the change in y on the function. And dy is the change in y on the tangent line. Now a little review from yesterday. We calculated dy by taking f prime at x times dx. Okay, and dy was an approximation for delta y, the actual change. So this is an approximation. This is the actual. All right, now the approximation will be, this is something I'll likely get to in the notes here, but will be an overestimate if f prime at x, f double prime at x is less than 0, meaning that it's concave down. So if the function is concave down at our x value, then our approximation is an overestimate. Likewise, the other way around, if our function is concave up, so f double prime at our x value is greater than 0, then it's an underestimate. We'll see an example of that in a little bit. All right, let's jump into this linearization information. Consider this function, f of x, which you'll see here in red. At the point x equals a, write the equation of the tangent line. Okay, so what is the ordered pair at x equals a? Well, that's pretty simple. That's a f of a. What is the slope of the function at x equals a? That's pretty simple. That's f prime at a. Therefore, the equation of the tangent line at x equals a would be y minus f of a equal to f prime at a times x minus a. Okay, so let's solve for y, and I'm actually going to call y this L of x thing. Okay, so here's L of x. L of x will equal f at a plus f prime at a times x minus a. Okay, so what does this kind of look like to you? What does that look like? Dx. And this right here, well, that's f prime at x, or at a, whatever that might be in that situation. Well, we know that f prime at x times dx, that's actually equal to dy. So L of x is actually equal to f at a plus dy. So if I want to find the local linearization at x, what this is actually estimating, I just rewrote that same thing, that's cool. L of x is an approximation for f at a plus delta x. Okay, it's an approximation for f at a plus delta x, so delta x in either direction. Okay, so let's get to using this in order to approximate some function value. All right, it says here, find the linearization equation for f equal to square root of x at x equals 100. Okay, so let's first find f prime. Well, f prime at x we know is 1 over 2 root x. All right, so that's equivalent to dy dx, which tells us dy, which would equal 1 over 2 root x dx. Okay, so now if we look back at our linearization equation, it told us that L of x equal to f at a plus f prime at a times x minus a. Okay, so let's build this. So L of x would equal f at a. Well, what is a? A is 100. Okay, so a is 100. So I want the square root of 100 plus f prime at a. So that's f prime at 100, which will be 1 over 2 times the square root of 100, which is equal to 1/20th. Okay, so 1/20th x minus a. So x minus 10. Okay, so that's going to be the equation. All this is the equation of the tangent line. Okay, so this is the tangent line equation to f of x equals the square root of x at x equals 100. All right, so let's draw the square root of x here. Not my best sketch, but we'll work with it. Here's 100. What would the output of 100 be? Well, if I take the square root of 100, I get 10, hence f at a. Okay, now I'm going to draw my tangent line. Both directions, not perfect, but that would be L of x, and that would help me to approximate values around that. So for example, you can see over here, I'm going to approximate the square root of 101. All right, since the square root of x is concave down, the square root of 101, or the approximate of that, here would be an approximate output for the square root of 101, would be an overestimate. Likewise, the square root of 99, that's going to be an overestimate for the square root of 99. So let's use this linearization function in order to estimate these. Okay, we've already determined that both will be overestimates. Okay, and the reason for that is because the concavity of the square root of x. So let's approximate the square root of 101. Whoops, 101. Well, I know that the square root of 101 will equal, okay, actually, I'm sorry. Let me do this. Let me utilize my linearization model and show you how I'd like you to work this. Okay, so L of 101 is equal to the following. 10, which is the square root of 100, plus 1 over 20 times 101 minus, and this, I messed up my linearization model. That should have been x minus 100. My bad. I cleaned that up. All right, so 101 minus 100, right? Because delta x here is 1, right? That's the change in x. Okay, so L of 101, or the linearization output for x equals 101, would be 10 plus 1 over 20 times 1. All right, so my approximation of the square root of 101 is that the square root of 101 is approximately 10.05. Okay, so of course L of 101 is not equal to but is an approximation of the square root of 101. Therefore, according to my calculations, the square root of 101 is approximately 10.05. Okay, let's do the same thing for the square root of 99. Okay, L of, oops, let's go blue. L of 99. Wow, come on now. L of 99 will still be square root of 100, which is 10, plus 1/20th of 99 minus 100. Okay, so that will be equal to 10 plus 1/20th times -1, which is 10 minus 1/20th, which ends up being 9.95. 9.95. Okay, now again, this is what the approximation is for the square root of 99. Therefore, this is an approximate, like I said, square root of 99. So the square root of 99 is approximately equal to 9.95. Okay, let's look at calculating this using our device. That moved on me. All right, using our calculator to see how accurate our estimate actually is. So the square root of 101, using the calculator, comes out to be 10.04987. It's really pretty accurate. Okay, and likewise on the other side of things, the square root of 99 is 9.94987. Equally as accurate on both estimates. Okay, now again, the further we got away here from x equals 100, the worse the estimate. So if we were to approximate 100, square root of 100.1, okay, it would be much more accurate. Even though this is very accurate, it would be more accurate than that. So the smaller delta x, the better the approximation. All right, a couple AP problems, non-calc on both. The approximate value of y equals the square root of x squared plus 3 at x equals 1.04 obtained from the tangent to the graph at x equals 1 is what? Okay, so let's lay out our linearization equation. L of x will equal f at a plus f prime at a x minus a. We gotta determine a, we gotta determine x, we gotta determine a derivative, all that good stuff. So a is gonna equal 1. A is gonna equal 1 because that's the value that's easy to calculate. All right, I'm not trying to approximate f of 1. I already know f of 1. So L of x will be equal to f at 1 plus f prime at 1 times x minus 1. Now, what is our x value? Well, our x value that we're trying to approximate is 1.04. So our goal here is to find an approximation using the tangent line, that's what L is going to mean, of f of 1, excuse me, of L of 1.04. So if I plug in for x a 1.04, what do I get? I get 0.04. And just so you remember, this right here is delta x, right? That's our change in x. So from 1 to 1.04, that's what we get. All right, so let's work the derivative. Let's plug in a value. So L of 1.04, f of 1 will be the square root of 4, which will be 2, plus f prime at 1. We'll gotta find f prime. It's gonna require the chain rule. So that'll be 1 over 2 root x squared plus 3 times the derivative of x squared plus 3, which is 2x. So f prime equals x over the square root of x squared plus 3. Okay, so f prime at 1. F prime at 1, if I plug in a 1, I get 1 over the square root of 4, which is 2. So I get a slope of the tangent line of 0.5. Now, 0.04 is the same as 1 over 25. 1 over 25. Okay, so our tangent line will tell us that y of 1.04 is approximately equal to this output. Therefore, this is our actual, can be approximated by plugging in all the values that we've done above. So that's going to be 2 plus 1/50. 1 divided by 50 is 0.02. So our tangent line would approximate to 0.02. All right, so our actual can be approximated by that number. Looks like our answer here is B. All right, let's look at example 3. Let f be a differentiable function such that f of 3 is 5, f prime at 3 is -2. If a tangent line to the graph of f at x equals 3 is used to find an approximation to a 0 of f, that approximation is blank. Okay, this is interesting. Let's build this. So let's use, again, our linearization model in the following way. Okay, and let's see what we know. All right, so if a tangent line to the graph of f at x equals 3, okay, that means that the point that I'm using is L of x, f of 3 is 5, f prime at 3 is -2, x minus 3. Okay, so now what it's asking me is not for an approximation of an output, it's asking me for an approximation for an input such that we get a 0. So I want this to equal 0. Right, the 0 of f. Let's approximate the 0 of f. So I'll help you visualize it in a moment here. Oh, I'd put plus minus there, that's cool. What we want to do is we want to solve for an x value such that the tangent line crosses the x-axis. All right, so I'm looking for an x-intercept. Let's subtract 5 divided by -2. So that'll be 5/2 is equal to x minus 3. I'm going to add, it looks like 3 to 5/2. So 2.5 plus 3 equals my x value. So x would equal 5.5. All right, so let's visualize this. All right, let's draw a function. F of 3 is 5. Okay, the tangent line at 3 to this function. I don't know what the function looks like, but I know that the tangent line looks like this, right? It's got a slope of -2. Okay, well, I don't know what the function looks like. Could it look like this? Sure. Could it look like this? Sure. I don't know. I have no idea. However, I can project my tangent line to where it would cross the x-axis. Now, would it be the exact 0 for f? No, but it'd be an approximation. So my tangent line at 5.5 ends up equaling 0. So this would be x equals 5.5. All right, that's an interesting one. Again, it's an approximation because if the graph took on this sketch or that form, clearly those two are off, right? And the other could end up wherever it ends up. So again, that's an approximation for the 0 of f. All right, let's do one more example. Okay, I lied. 2 more examples. Example 4, AP problem from 2007. Let's read it out here. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function, r of t. Okay, where t is measured in minutes. For the interval from 0 to 12, the graph of r is concave down. Okay, that's going to be helpful. That's going to probably help us with over and underestimate. The table above gives selected values of the rate of change r prime of t of the radius of the balloon over that time. The radius of the balloon is 30 feet when t equals 5. Okay, so some information that we want to be aware of. Looks like r of 5 equals 30, and I'm just going to make an educated guess here and say that we're going to use r prime at 5, which is 2. Okay, it says estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Okay, so L at 5.4 would be equal to r of 5 plus r prime at 5 times t minus 5, in this case 5.4 minus 5. You can see the change in t there showing up immediately. So our approximation is going to be built off of this. That'll be 30 plus r prime at 5, which is 2, times the change in t, which is 0.4. So it looks like 30.8, let's use units here. Estimate the radius of the balloon when t equals 5.4, so the radius is feet. Okay, so L of 5.4 gives us 30.8 feet, so the radius is approximately 30.8 feet at time t equals 5.4 minutes. Okay, now it asks, is your estimate greater than or less than the true value? Okay, so L of 5.4 will be, let's see here, we have concave down, so it would be greater than r of 5.4. Again, approximate, actual. Okay, since, I was about to put when, since r of t is concave down, on this interval from 0 to 12. Okay, outstanding. Let's look at number 5 here. Example 5 from 2002. Problem number 6. Let f be a function that is differentiable for all real numbers. The table above gives values of f and its derivative f prime for selected points of x in the closed interval from negative 1.5 to 1.5. The second derivative of f has the property that f double prime is greater than 0. Okay, that's going to make our tangent line approximation an underestimate. Write an equation for the tangent line to the graph of f at the point where x equals 1. All right, so let's do that. That'll be relatively easy. All right. So in order to do that, 2 things I need to know f of 1. I don't know if I have that. Do I have that? Yes, I do. F of 1 is negative 4. Okay, so that'll be y minus a negative 4 and x minus 1. I just need the slope. What is f prime at 1? F prime at 1 is 5. All right, so there's my tangent line to the graph of f. Use this line to approximate the value of f of 1.2. Okay, so I'm going to take and rewrite y as L of x. Subtract the 4 over, add it to 5 times the quantity x minus 1. So you can see the linearization model take shape. So f of 1.2 is approximately the same as L of 1.2, which is negative 4 plus 5 times 0.2. Right, I'd take 1.2 minus 1, which gives me delta x, which is 0.2. So L of 1.2 is equal to negative 4 plus 1, that would be, right, 5 times 1/5 would be 1. So L of 1.2 equals negative 3. Therefore, f of 1.2 is approximately negative 3. All right, is this approximation greater than or less than the actual, and give a reason for your answer. All right, L of 1.2 is equal to negative 3 is an underestimate of f of 1.2 since f double prime of x is greater than 0 on the interval from negative 1.5 to 1.5. All right, guys, that's it for this lesson. If you got questions, see your teacher. See you in the next video.